Hello, it's Keith here, and this is lesson 92 of the platform-specific series of my Z80 assembly programming tutorials, and this is the second part of the CPC MaxTile tutorial. MaxTile is my software tilemap code. You can see it here. It also draws simulated sprites. Now, what we're going to look at today is the parts of the code that do the fast fill. That's this here, which is where an entire tile is filled with just 2 bytes of source data. The double height, which is where an entire tile is filled with 8 bytes of data, so it's reusing the same normal tiles, but it's drawing each line twice. In this case, it's been done for a cute double height effect, but it's really intended to save memory. When I did my Suck Hunt game, I had a stupid introduction, which was a parody of the Operation Wolf game. I didn't have enough memory to do the animation tiles I wanted, but by halving the height of some of the less important data, actually I think it was the entire data, by halving the height, the effect was almost identical, and it saved literally half the memory. And for a silly joke that it really wasn't worth making the game a multi-load game to fit the joke in. So as I say, halving the height of the tiles actually makes them easy to draw still, and it means that you're using half the source data, which in some cases may make little to no effect. But it's also slightly faster as well, which added bonus. The other thing is there is some pseudo transparency. Now this character here, you can see, looks different to this one, and that's because it's using something I refer to as byte zero transparency, which is where if an entire byte contains 0 bits, the entire byte is 0, it's not drawn to the screen, but everything else is. This was the kind of transparency used to a great extent in Chibi Akumas. It's fast to do, it's simple, and it gives a pleasing effect. It does give a kind of a black border around the characters, but I think that works quite nicely with my cartoony characters. Now, that's the other thing we're going to look at. And then finally, the other thing is the half shift versions of the code. The regular code is optimized for an 8 pixel alignment. So you can see here the tiles go to the entire edge of the screen. That's 8 pixel alignment, but we can, if we can do a Y shift of 4 pixels, we can have our characters moving smoothly and a partial scroll. You can see there's some corruption around the edge of the screen. It's really intended that there would be a 4 pixel border filled in around the edges of the screen. I've just not got it enabled in this simple example. Now, that 4 pixel shift version means an entire second copy of all of the main routines, and the reason there's an entire second copy is all of the memory calculation code has had to be rewritten for that shift, because the code is highly optimized for the VRAM layout, and that layout doesn't work very nicely with a 4 pixel shift. Anyway, let's go over to our code. Let's take a look at what we've got. Now, just quickly, we're going to recap the regular routine for comparison. So here is the regular routine, the unflipped routine. So here we are removing the least significant bit and putting a 0 in. The least significant bit is the update flag that flags that this tile needs to be redrawn. What we're doing then is we are taking the first byte, the low byte of the HL source tile number, and getting the high byte, and then we're adding the DE address, which is the source pattern data, the bitmap data that we're going to draw to the screen. Now, the bottom 4 bits we're ignoring there. That's because we're effectively multiplying by 16 without multiplying. 16 bytes per tile, you see. And then we're moving that to the stack pointer because we're using stack misuse. We are popping the bitmap data of the source tile, and we're drawing it to the screen. When we want to move down a line, we need to add 800 to the HL pair in hexadecimal. To do that, we load C with 8. We're backing up the H part of the HL pair and also loading into the accumulator. And then to add 800 to the HL pair, we simply add C to the accumulator and move it into H each time. And we do that 8 times to move down the 8 lines, and then we go back up to the start of the tile by reloading H from B. With regards to drawing the bitmap data, we draw it in a zigzag, moving across on the first line and then backwards on the second line, and swapping the order we draw the data. So the first time we load E and then D and increment L, and then the second time we do D and then E and decrement L. Third time, E then D then increment L, D, E, decrement L. So we're doing a zigzag and we are writing the bitmap data. That's the basic fastest version, or at least fastest if we're filling all of the bytes with different data. Now, if we're not flipping the tiles, we end up drawing a custom code. Basically, at this point, we are going to have to do some kind of custom routine. So at this point, we know that the update flag was 1 because we wouldn't be drawing a tile otherwise. The program bit was 1 because that defines the advanced routines. The X and Y bits was 0, no flip occurred, and we're now into these so-called custom routines. Now the bits marked BB here are actually in this case the program code. There are 3 programs defined. There is room for a 4th, which I'm not using, so you can write your own if you want, and that's what we're going to use here. Now that leaves 2 remaining bits, and by the definition I'm using here, those are defined as being a possible extra 2 bits of the tile pattern address. So these would be effectively the top 2 bits of the address. So we're not actually using them in most cases here, but as I say, that is what they are potentially used for. So what we're doing here is we are taking those 2 bits and moving them into the H register here for later. We are then getting the 2 bits that define the program number, and we are going to see what they are. Now, if those 2 bits are 0, then this is defined as a solid fill tile. If those 2 bits are double 1, then this is an empty tile, a transparent tile, either completely transparent, nothing in the tile at all, or a partially transparent tile with that byte 0 transparency, as I call it. If we fall through here, then this is either 0, 1 or 1, 0 is the program. Now I'm defining this as 0, 1 as the double height, and you could put your own 1, 0 code in here if you wanted. I've not done that, but you could do. And then what this is going to do is effectively take the HL address and multiply it by 8. Why 8? Well, because the tiles are 16 bytes, but we're going to use each line twice, and so we're only going to use 8 bytes in total. So we're multiplying by 8 here. We're adding the DE base for our pattern data, because we're using the same pattern data, loading into the stack pointer as before. And what we've got here is almost the same as the previous example, that basic example I showed you earlier. Popping 2 bytes out of the stack, the source pattern data, drawing the first line to the screen and moving down a line. But this time we don't pop any more data yet. We use the same pair for a second line. And then, so basically we're popping every 2 lines. And so basically we're using the same data for 2 lines, 8 bytes in total for the 16 byte tile. As I say, it will actually be slightly faster because we're popping less data, mostly the same, though, pretty much all the same code, but slightly faster. So, you know, there's some benefit there. And that is the double height version. Now the fill version, very similar really. All of these, to be honest, pretty similar. Now the fill version, we're actually using the pattern address as is. The fill patterns are assumed to be at the start of the pattern data. We could multiply by 2, but actually if we're using checkerboard effects, then using in-between values is also valid, because one version of the combination of patterns and the next one, if you shift along, they will create different effects, and so using every combination of the bytes there is perfectly good and gives nice results. Now the way that this works is, again, very similar to before, but this time we're only doing 1 single pop. Now what we do is we use the E byte for both of the bytes of the first line, and then the D byte for both of the bytes of the second line. Each byte defines 4 pixels on the CPC, and so we're repeating that byte twice on the first line. That gives this checkerboard effect, and that's where sort of alternate pixels are one color. On the first line, maybe the first pixel is white and the second pixel is black, third pixel white, second pixel, fourth pixel black, and then on the next line it's the opposite way round. And so by using the alternate bytes for alternate lines, that gives us the ability to do that kind of effect. And you can also have a stripy vertical effect if you want. So I think that's a good way of doing things. And as I say, only 1 pop per line, so it's going to be faster than any of the other routines. But the actual movement routines are basically the same. Okay, now the final one we've got is the transparent kind. Now there is a bit of a special case here. So basically, this is either an empty tile, which is a tile with nothing in it, which isn't drawn at all, which is of course extremely fast, or a transparent tile, which is extremely slow actually. So a bit of a combination. Anyway, what we're doing here is we're loading the second byte. The first byte is the program one, and as I say, a few of the bits. The second byte is the tile number, the low byte of the tile number. Now we were going to compare this to 255. If this is 255, this is a completely empty tile. Rather than comparing to 255, we do an inc A. That is slightly faster. That's a single byte command. CP255 is a 2-byte command, and so doing an inc is going to save us a byte here, and saves a little bit of performance for this potentially common routine. Now if that byte didn't contain 0, then that byte was not 255. In that case we're going to use the transparency routine, but if it did, then this is an empty tile. We're flipping to the shadow registers here to make sure things end up the same way as they did as the other routines, but in that case the tile's completely empty, we aren't going to draw it. Now here is our transparency routine. So the transparency routine uses the same pattern data as before, and so we're taking the top byte which is actually the low byte in the case of transparency. It's a bit of a special case. The 2 bits that we loaded in before are the high byte, and so we're then going to multiply these by 16, and then what we're going to do is going to add the DE pair as before, the pattern data. We're using the same pattern data. And then what we're going to do is we're going to have the transparency effect. The transparency effect is simply we read each byte in from the source data, popping it out of the stack, and then we compare it to the value 0, in generally speaking. And if the value, if the byte read in is 0, we skip over the draw command, as you can see here, and so that those skips are there. But rather than having CP0 here or anything like that, what I'm actually doing is the byte that's being compared to is being loaded here. We're actually then moving that into the accumulator, and that's so that we can compare alternately between D and E here. The reason I'm loading it into C here is forward thinking. With Chibi Akuma's the original game, I used the byte 0 as transparency, but then later I wanted some characters that used and graphics that used the background color, the black background color, as part of their color, and using the 0 byte wasn't very convenient then. So what I then did is I used a rainbow byte, which is where the first pixel is 0, the second pixel is color 1, third pixel color 2, fourth pixel color 3, or the other way around, and that's a very rare pattern, and so that was more convenient. And so if you want to do something like that, you could use self-modifying code to switch this byte before you run this routine, and it will do the same, and now you can use byte 0 as an actual pixel byte. So that's why I've done it like this, planning for stuff that I think I will need later on. And so this is that transparent effect here. So basically, again, we're loading in D bytes from the DE pair comparing to E. The accumulator has been loaded in with our transparent byte, 0 in this case. And so if the bytes that are read in match that, we're skipping over the draw routine. Otherwise, we're writing them to the screen. We're moving down the screen by adding 8 to the HL pair, 800 in hexadecimal, adding 8 to the high part there, and at the end we're resetting, and then we're done. Now, as I say, this is going to be quite slow. Transparency is something I would try and avoid. The benefit of breaking up the image into 8x8 tiles is you can have transparency around the edges where it may be needed, and not in the middle where it certainly or possibly isn't. So that is definitely an advantage. So that's the last of the tile drawing routines, the basic ones at least. Now the last thing we're going to discuss is the 4 pixel shift. As I say, there's an alternative version that allows a Y pixel shift of 4. An X pixel shift of 4 is fine because the bytes in memory go consecutive anyway. So moving across the screen by 4 pixels, you just increment the draw position in the HL pair by 1, and that does it. But the Y position, because of the optimizations of those get next line routines within the tile drawing, won't work. And so at the start of our draw tile map here, before we start drawing a strip of tiles, we're checking to see if we need to actually use the alternate code, and we're branching out to do strip half. And this is an alternate version of the next section that runs this alternate drawing routine. Now, we could have used self-modifying code to get the same effect, but I figured we don't want to branch out every tile, but branching out every line means that we're getting reasonable efficiency here, and not having too many more conditions and things. And I've avoided using the self-modifying code for this rather odd module. So that's what we've done. Now the code itself is actually fairly similar. I'm not going to go through all of the versions because I'm just going to go through the main one, because they're basically all the same, give or take. But basically the first things we do are the same. Here we are reading in the first byte here. We're clearing the update flag, and we're masking to get the top 4 bits of the tile number, which is effectively the offset for the tile pattern data in DE here. We're moving that to the stack as before. Now, the problem comes at this point because basically, for the first few lines, because we're 4 pixels down, the first 3 lines, we don't need to worry, we can do things the same. But after the 4th line, we've now gone over the boundary, and because we're adding 800 to the HL pair each time, we end up with a wraparound effect. And so the last one, we actually have to do basically a correction, and we have to update H and L both to correct for this, and so that's what we're doing there. And then we can continue onwards, and then finally we're having to undo the changes here. And that's why I've used these second versions of the code, because that 4th line calculation is a bit of a rotter, and to do that kind of check every single line, if we did that every single time here, it would ruin the performance of the code. And so it seemed more sensible to me to have a second copy of the code if it was necessary to have that functionality. If it's not, then you don't need it. If it is, then you can use this. Now, all of these are unwrapped loops, of course. There's no loops really here at all, and that's again because loops waste processing power. And this is the place, if there's any place in my experience that you're going to save processing power, it's in these kind of intensive drawing routines. You'll often see people talk about optimization and things, and they'll say, "Oh, here's all these tricks you can do for optimization," like that thing of if you want to compare to 255, doing an increment and then comparing to 0, and that will save you 1 byte. And it's like, yes, it certainly will. You'll never notice the difference though, and you might spend days writing that and debugging it, and good luck to you if you do, but you'll never notice the difference. It's in these drawing routines you will notice the difference, and that's where you want to focus all of your efforts optimization wise, and where you want to waste memory and have unwrapped loops and second copies of code and things like that to gain the efficiency, because this is the place. Those tile drawing routines for that main unflipped tile will be drawn 768 times per screen if the entire screen is redrawn. So that's where you will gain your savings, and that's the way you want to focus on trying to find the savings. Don't bother looking at your joystick routine that's run once per frame, because even if you find the saving, you'll never notice it. Anyway, go to the website down at the source code, the build scripts. I forgot to tell you the name of today's example. That second one is CPC MaxTile half shift. The main one is CPC MaxTile normal. So, go ahead and download those, and as I say, use them in any way you can. Take them apart, take bits out of them, get ideas, and you're welcome to do so, even if your projects are commercial. That's what it's there for. Hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.